So projectile motion questions are called projectile motion questions because we have things most of the time flying through the air, and so the name that we call those things flying through the air are projectiles, you know, like cannons and things.
Yeah, and so it doesn't say that he jumps off or anything, so I'm guessing it's just kind of like a falling question.
So it said that he was running with some speed, right?
2.4 meters per second.
And did I hear you say he like jumps horizontally, or?
It just dives out horizontally.
Okay.
So
Yeah, that is important to pick up on those little verbal clues. So when it says that he dives out horizontally, that's important because we know that when he dives, he's just diving straight out as opposed to, you know, going up and out at an angle. Which are two questions, both those questions we can answer, but it's important to know which type of question they want us to work on, because otherwise we're going to get the wrong answer. So if here's our dot representing our diver right before he jumps, his trajectory would look something like this. He'd follow this nice arc, and then here's the water below. So there's two really important points in his trajectory. There's the initial point, so right after he leaves the platform, and then this point right before he hits the water. Those are the 2 points that we're most interested in. And so what we can do just to organize our thoughts and organize our information is label both of these points with some variables. So here, what is the question asking?
how high is the cliff?
How high?
Yeah. And then this follow-up question is how far from the base did the diver hit the water?
Okay.
So we're doing the X, we'll do an X and the Y. Yeah.
Is that the same as horizontal distance, the X? Yeah, okay, good.
Yeah, so we'll call the height, you could call it H, but just to, you know, stay consistent, I like to call it Y because it's along the Y axis.
Right.
And then same thing here, we could call it D or something for distance, but might as well just call it X because it's running along the X axis. And so those are variables that are just really widely used. So this point we can label with a number of variables. We can say, well, he had some initial Y value. He had some initial X value. He had some initial speed in the X direction. He had some initial speed in the Y direction. And he had, you know, some initial time when we stop our stopwatch. So it seems like a lot, but just 5 variables, and then we'll have the same variables down here, but instead of putting a not symbol, we'll just put the absence of a not symbol to represent the final. So we'd have Y, X, Vx, Vy, and T. And this will help us just get an idea of what we know and what we don't know.
Okay, so we do this for each dot then.
Cool. So let's see what we know. T naught we can pretty much always call 0 seconds because we're just saying we're going to start our hypothetical stopwatch, you know, right as soon as he leaves the platform. So 0 seconds, and then it's ticking the whole time until he hits. V naught in the y direction. So what is his initial speed in the up-down axis, right as he jumps off? 0, good. Because he hasn't started falling yet. The next instant he'll have some speed because gravity will have started to act on him.
Right,
But
but
for
right
right now,
on the board, he's not falling.
well, we're looking at the instant just after he leaves the board.
Oh, okay.
But still, it's 0.
Is there a speed right after though? That? Okay.
You know, the very next instant he'd start to gain some downward velocity because gravity starts to pull.
What
So I mean,
about like for this example, is that the same as it starting out at 0, or would I use this as the...
no, for this one, it would have some positive initial y velocity because it starts going up.
Okay.
But in this case, since he's
going straight out.
yeah, doesn't have it. So this marker, when I drop it, it looks like it instantly has speed, but in reality, for one instant, like that instant right after I drop it, it has no speed in the downward direction. It takes, you know, time for gravity to start acting on it and start pulling it down. It happens, you know, instantly, but for that very, very, very first instant, we say 0 meters per second downward, right? That's not the case with his x velocity because we know that he had a running start. So at this point, he already had some x velocity. And what was that velocity?
2.4 meters per second.
So Vx naught we'll call 2.45?
4
2.4
meters per second.
meters per second. Now y naught, so his initial y displacement, we can't say because we don't know how high up he is. That's what we're looking for. So we're going to leave that blank for right now.
So that's what we're looking
But x naught, we can call it whatever we want. The most intelligent thing is to call it 0. And we'll just say this is our 0 mark, and then anything beyond this starts having some positive value. So here we'll say 0 meters. Here, we can fill in a y value because we know this is the instant right before he hits the water. We'll think of the water as our 0 mark. So we'll call this 0 meters above the water. X here we don't know. That's what part B is going to be asking us for. Velocity in the x direction. Does anyone know what that is? His final velocity in the x direction?
Gravity. Well,
Gravity, it works in the y dimension, right? So in the x dimension, there's nothing that's causing him to speed up or slow down. So his final x velocity will be the same as his initial x
0.
velocity, 2.4.
Oh, okay.
Okay. So that's constant.
So the whole time that he's falling, he'll be going 2.4 meters per second in the right direction, or in the positive x direction. His final y velocity, we don't know what it's going to be because this whole time gravity's been acting on him, so it's going to be some non-zero number. It was 0 before, but now it's going to be some non-zero number. Can't say what it is. Same thing with t. We know it's going to be something above 0, but we don't know a value to put there yet.
And x we don't know as well. Okay.
Cool. So now that we've got it mapped out really well, what we know and what we don't know, we've got a picture. Now would be a great time to write our kinematic equations and just ask ourselves which ones we can use and which ones we can't use, given the information that we know. So our kinematic equations are x equals x naught plus v naught t plus 1/2 at squared. And these x's could just as correctly be written as y's. We can say v equals v naught plus at. And we also know that v squared equals v naught squared plus 2a times change in x. Again, that x could just as easily be a y. So right now, the first part, they want to know how high the cliff is. So let's go ahead and rewrite these as y's, since this first question they're asking is a y question. So there's two equations that we can look at that involve y, which is good because that's what we're looking for. Here, this equation, v naught, we know what that is. In the y dimension, it's 0. We know what acceleration is in the y direction. We forgot to write that, but it's negative 9.81 meters per second squared. That's gravity. Negative because it's going in the downward direction. So we know what a is, we know what v naught is. We're looking for delta y, so we don't know it, and we also don't know v final. So this equation we can't use because there's two things that we don't know in it. So let's look at the other one that involves y's. We're looking for y naught. We know y final. We know v naught. We don't know time. We know acceleration. So again, we're going to do the same problem where there's two things that we don't know. We don't know time and we don't know y. So now we're forced to look at our other equation. Even though it doesn't have what we're looking for, we can still solve it because we know, no, we can't solve that one either.